Right. So Lagrange multipliers is a technique used to solve a particular kind of optimization problem, namely optimization problems where you have a constraint. Okay. So here's kind of a graphical way to reason about why the Lagrange multiplier method works. So suppose that we are on the point Q on this constraint curve, right? G of xy equals 0, and we want to maximize the value of the function f. Well, what you can do um, is that, notice, if you take the gradient of f at the point Q, you'll get some vector pointing in some direction. That direction is going to be the direction of greatest ascent, right? That's what it means. That's the geometric meaning of the gradient at a point. Is it's a vector pointing in the direction of steepest ascent, whose magnitude is the actual change that you would get if you moved 1 unit in that direction, right, back in whatever section that was. So notice that, yeah, we have a particular direction. Now, if we try to follow that direction, we can't follow it exactly because that would make us leave the curve. But what we can do is notice that we can move towards that direction while staying on the curve. And doing that in this picture is going to move us to the right. And eventually, it will move us to the point P, where the gradient will actually be perpendicular to the level curve. Well, it's not really a level curve. The constraint curve. Yeah, so it'll be perpendicular to the constraint curve, meaning that if we were to try moving in the direction of the gradient, it would completely leave the curve, and we have no like ability to adjust left or right and have it increase anymore. So you can see that we hit a maximum for the function f if we are to satisfy the constraint g. Okay, and what you can reason about this is then that the gradient of f at this point and the gradient of g at this point have the relationship that they are both orthogonal at that point. Or am I saying this wrong? The gradient is orthogonal to the level curves of f as well as to the constraint curve g, which means that they are pointing in the same direction, but maybe with opposite magnitude. And so that's why we end up with this equation. So this visual depiction is to try to explain why we have this as the equation, or the system of equations that we solve for doing the Lagrange multiplier method. The Lagrange multiplier method boils down to rewriting this as a system of equations and then solving for the values, the points that satisfy this relationship. Lambda is a scalar, a number, that is called the Lagrange multiplier. You won't Usually you won't need to solve for Lagrange for lambda itself. Usually it's kind of like an auxiliary thing that's used to relate the two uh, sets of sides of the equations. We'll see that in the examples. What else am I doing here? The strategy to optimize. Yeah. So right, we end up solving this system. So this is the I think I was looking at a book and it called this the Lagrange condition, and this is the constraint condition, right? We're enforcing that the points that we're looking for, they satisfy the condition. Okay, and I know from a previous semester that I taught, Ivan Blank called these the constrained critical points. So, and I kind of like that name, so I'm also going to call those the constrained critical points. They are the critical points when you consider yourself constrained to the curve g, right? Or g equals 0, I should probably say. Okay, right. And then once you find all these constrained critical points, you do the same process as you did with optimization. You have to plug those points into your function f in order to determine the maximum value and minimum value. Okay, because these critical points are where where the max and min can occur, but you still need to test them to see what the actual values are. Okay. Some additional remarks on this method. So this method is actually quite general. you have that, in fact, this method can work for any number of variables, although we'll only see that this for two variables and three variables. Our functions will only be of, at most, three variables, but perhaps in more real-world type of problems, there may be more variables. Also, you can have multiple constraints being satisfied. Now, this wasn't on the homework set that you have. You only have one constraint. I think I've, at one point in the past, done a problem with two constraints. But so what happens with, if you have multiple constraints, is you end up needing to add another multiplier for an additional constraint. So here is a sketch of an example, I suppose. If you have two constraints, g is equal to 0 and h is equal to 0, two separate functions that constrain the solutions that you're looking for, well, then using the method of Lagrange multipliers, you'd have to introduce two parameters. Well, the constraints would have two parameters. So ordinarily, you just have this term, lambda times gradient of g. But then with this additional constraint, you add on another scalar and another gradient calculation you're doing. So mu times gradient of h. So this ends up being a system of three equations on, well, five equations total. So the gradient calculation here was going to be three different equations, one for each component function. And then these two additional constraints give you a system of five equations. And technically five unknowns, because you have x, y, and z, and lambda and mu are also unknowns. They're variables. They should be some numbers, but we don't know what they are. So yeah, five equations and five unknowns. So there can be solutions. Yeah. Okay. Right. So these problems are computationally a little bit, well, maybe not computationally, but they're tricky in the sense of doing the casework. I would say, like, it's a bit hard to keep track of the line of reasoning, and so I've done my best to make it make sense, but it involves casework, and you have to kind of carefully keep track of things. And so I thought it would be helpful to not just give you the answers, but also tell you if you do the process correctly, you'll get the boxed number of critical points if you solve the system of equations correctly. So you see that with 359, problem 359, it's 14 critical points. Maybe I can, should I say, actually I forget how it, I think it was definitely 2 to the third, and then I think it was plus, well, 14 minus 8, so 6, but I think it was the 6 from a 2 times 3, or was it something else? I think it was like this. So if you count the points up, you'll count it up in this way. You have like two. You'll see if you do it correctly. Okay. And the answers, well, I don't feel too bad about giving the answers away. Because the main difficulty of these problems is actually doing them logically correctly. I mean, I guess in the real world, you'll probably hand this off to some piece of software that will just find the all of the solutions to a system of equations. There are programs that do that, like Mathematica. But here, the exercise is more in making sure that you can carefully do it, I think. Yeah. All right, so let's look at some examples. So first off, we have, I think I have two simple examples to show you, and then one medium difficult, and then two others that are tricky, as I mentioned, which more closely follow the homework problems that you have. Okay, so starting with this one. So find the minimum of a function subject to this constraint. So we start by writing, by expanding out the condition that gradient of f is equal to lambda gradient of g, right? I should probably mention where is g, because that may not be immediately clear. The way that you create g is you just you take your constraint equation and you move everything to one side. so that the other side is equal to 0, and that is your constraint. So in this case, g is g of x, y, z is equal to x plus y plus z minus 1. Right, so that is the process that you take. And so now that we have this g, we can take the gradient of it pretty easily. You see that the x, y, and z derivatives are going to be 1, 1, and 1. It's really very quick. And then for this function, x derivative is 2x, y derivative is 2y, z derivative is 2z. Okay, so that gives you this equation up top. And then you have the constraint there as the second equation in the system. And then we expand this out. So this vector equation, I guess you could call it, this is actually 3 equations in one. So yeah, these 3. And now we go ahead and we solve this system. So the difficulty of these problems lies in how you go about solving a system of equations. Sometimes there is a clear-cut process to do them, but with these, because the equations don't have to be linear, it can be a bit more just cleverly noticing that things connect together nicely. So, for instance, here, because all of these have the right-hand side being the same, you can set them all equal to each other. And then you can get rid of the 2's that are redundant. And so then you end up immediately being able to conclude that x equals y equals z. Applying that knowledge to this constraint equation, this reduces to, well, 3x is equal to 1, therefore x must be 1/3. Okay, so that gives us the single critical point, 1/3, 1/3, 1/3. And then you can plug that back into the function f in order to figure out what the value is. So I guess I do that here, and I get the value 1/3. And then, well, just to check things, we want to verify that this is indeed a minimum, because the problem asks us to find a minimum. We found 1 point, but this process, technically, we found critical points. We don't really see directly that this is a minimum. So what we do instead is in order to verify that it's a minimum, we just grab any point on the curve, on the constraint curve, and we plug it in and just make sure that this is indeed a minimum. So an easy point to plug is 1, 0, 0. Plug that into here, you get the value 1, and certainly 1/3 is less than 1. So that shows that, yes, 1/3 is actually a minimum for the function. Okay, that's a pretty easy example. Next example. So we've got the function f equals 5x minus 3y, and we are constraining ourselves to this, circle. Okay, so yes, again, we take the gradient. Maybe, I mean, when I do these things by hand, I normally do actually write the whatever this equation is called, Lagrange condition. I should look it up and remember it. But yeah, so this equation, I normally start by writing this out and then I do the calculation, but it's up to you. All right, so the x derivative of f is going to be 5. Yes. The y derivative of f is going to be -3. Yep. The x derivative of this constraint. Okay, I will also just for clarity's sake, I will write this x squared minus y squared minus 136. So that is the constraint equation. And then or function, I should say. And then you take the gradient of this. So you get 2x for the x derivative. You get minus 2y. Okay, good. Plus. 2y for the y derivative. And then you have the constraint down there. Then this vector equation is actually 2 equations. So now we have a system of 3 equations and 3 unknowns. X, y, and lambda are our unknowns. Okay, so now we try to solve this system. So let's see, how did I do that? First I noticed that y cannot be 0. Right. Or not y, lambda. Lambda cannot be 0. So that's because if lambda was equal to 0, then these 2 equations would be impossible. Yeah, 5 equals 0 is definitely incorrect. So lambda cannot be 0. Okay, well, since it can't be 0, and this is one of the things we need to be careful about when solving these systems, the difficulty is to do with making sure that we don't miss any conditions, and so we have to be very careful with our assumptions. One of the assumptions we have to be careful about is that we never divide by 0, or we never divide by a quantity that could be 0. If we ever try to do that, then our casework actually splits into two possibilities, one where it is equal to 0 and one where it's not equal to 0. And so that kind of makes working through all the possibilities a bit difficult to track. Okay, so yeah, we have to try to keep track of things carefully. All right, so but we have a nice situation here where we can immediately conclude that lambda can't be 0. Okay, so that's good because that means we can divide and we don't need to worry about that. So we go ahead and we do that, and by doing that, we end up solving for x and y in these two equations. It gives us this, these guys. And now we can plug these into the constraint. Okay, so we do that, and you get 25 over 4 lambda squared plus 9 over 4 lambda squared. And then you can combine this to make it a bit simpler. There's a cancellation of 2. This would be 34 over 4, and so that simplifies. And then I can solve for lambda. Now notice, when I solve for lambda, I have to be careful. It's going to be plus or minus 1/4. Okay, so that's two possible values of lambda, from which we can then plug into these equations and solve for x and y. Okay, so if lambda is equal to 1/4, plugging it in, you'll get 10 and -6, right? And if you plug in -1/4, then, well, the signs will flip. Since lambda is to the first power. So you get -10 and you get 6. Okay. So that gives us two constrained critical points, and we plug them into the function, the original function f, to determine minimum and maximum. And well, so that's a calculation. Not too bad. All right. So yeah, those were easy examples. So hopefully that gives you some level of confidence with this process. Now it's going to get a little bit more tricky. So this one kind of leads up to it. This looks which problem was it? This looks similar to 359, but I actually have another version that is even more similar because the numbers are more complicated. It makes the case work a little bit harder. Okay, here we just have this constraint. Okay, and this is just a niceness condition. The issue is if you don't assume this, you can have really large negative values that will obviously make this go to infinity. You can have like -100, 100, and then 1 or something like that, and it'll be very negative. So just to make this problem make sense, we assume that x, y, and z are greater than, are always are positive or non-negative. Okay. So taking the gradient, the x derivative gives you yz, the y derivative gives you xz, and the z derivative gives you xy. So you can see those there. And then for the x, y, and z derivatives, they're just going to be 1 for the constraint. So you get this, and of course lambda. Okay, and the constraint is there, and then you expand this out to get a system of 4 equations and 4 unknowns. Your unknowns are x, y, z, and lambda. Okay, so let's see. The first thing I do is I set these two equations equal to each other. Since they have a lambda, we can set, since the right-hand side is the same, we can just set one equal to the other. So we have yz is equal to xz, okay? And then solving now, so, you know, maybe your reflex would have been to divide by z. No, that is not true because z could be 0. So this actually splits into two possibilities. All right, so the better way to keep track of this is to move the term to the other side and factor, and then you see clearly that either y is equal to x or z is equal to 0, right, in order for this equation to hold true. So we have two possibilities, and then I sort of break it up into these cases. So suppose that z is 0. Well then, by this equation, that means that lambda must be 0. Okay, so lambda is now 0. Okay, well that has made what am I doing? It's hard. I think. Oh yeah, okay. I see what I'm saying. Okay, the third equation is this guy. So, looking at equation 3. So we end up getting that xy is equal to 0, is what I should mention. So yeah, once you suppose that z is 0, then that means you can look at either of these two equations and you get that lambda must be equal to 0. Then, since this side is now equal to 0, that implies that x or y is 0. And so then we get another two cases within this case. I guess these are subcases of this case. Okay. So if you are in the case where x is equal to 0, well, then we have this constraint. But we're in this subcase where x is 0 and z is 0. So these two terms are both 0, so then y must be equal to 1 to satisfy the constraint, which gives you one critical point. So that's the subcase of x equaling 0. Now for the subcase of y equaling 0, well, the same reasoning holds. You have z and y equal 0. X therefore must be 1 to satisfy the constraint, which gives you another critical point. And I think I should probably just underline these to emphasize them. We're going to collect things at the end and evaluate everything. Okay, so that wraps up this case of assuming that z was equal to 0. So now we look back and we had another possible branch that we could take. We could have had that x is equal to y, right? So we now try that out and see what points we get. So assuming that y is equal to x, well, okay, so this time I plug things in. I replace, it looks like, I replace y everywhere by x in this to get this system. So in particular, it should be that two of the branches combined. Yeah, so these two equations became the same equation, xz equals lambda. And then you can see that, yeah, the xy became x squared, and then the x plus y became 2x. Yeah. Okay, so our system reduces to this, and so we're now considering this guy. Since these two have the right-hand side be the same, I can set them equal to each other. That's what I do next. And then I can solve for this. I can try to find the solutions of this. So the way I do that is, again, I'm careful about dividing by quantities that could possibly be 0. So I'm factoring. I guess I'm moving the xz to the other side, and then I factor out the x, and so I get that this is equal to 0. So either x is 0 or x is equal to z. Okay, and so now we have subcases again. If we're in the subcase that x is equal to 0, then to satisfy the constraint, which is this guy now, I'm thinking about this constraint. So if x is equal to 0, then z must be 1. Okay, and that gives me this point. If instead I am assuming that x is equal to z, if I'm in that subcase, then I believe this becomes 3x equals 1, right? 3x is equal to 1, therefore x is equal to a third, and so we're in the state, so we have to kind of wrap the setting back. So we're in the subcase where x is equal to z, and then also where y is equal to x. So x, y, and z are all equal to each other. That is how we end up getting this point. Okay. So, and then that's all of the possible cases when we do our kind of case-by-case analysis of this. So we found all of the solutions to the system of equations we started with. So just as a reminder, this was our system of equations, and it involved quite a bit of case-by-case stuff to find all the solutions. These are all the solutions, these 4 points. Okay, and now we're trying to find the minimum and maximum of the function f. So we plug all these points in, and you can see that happening here. F is a rather nice function. F is, I think, just, yeah, x times y times z. So calculating that is really easy, right? With these 3 points, it's immediately 0 because one of the factors is 0. And then this one is the only non-zero value. Okay, so we get that 0 is a minimum and 1 over 27 is the maximum for this function subject to the constraint. Okay. All right, so now let's see a slightly more bothersome version of this. So before we had a linear expression. Now we end up having 2's. Is that the difference? Kind of. Yeah. So because these were all terms of degree 1, the right-hand side of these equations was simple to work with. Once the constraint becomes a bit more complicated, you end up getting variables on the other side, and that should make the working a little bit trickier. And I believe that the way that your problem looks like, yeah, the x is also squared. You have different numbers, but the x is squared, and that kind of makes the cases a little bit different, but not too different from this version. So this is the more proper, similar version to 359. Okay, so computing the gradients of these two functions should be pretty straightforward at this point. Let's just make sure that we talk through it though. And of course, I'm solving this, right? Moving the thing to the other side. So 9y squared plus z squared minus 4. That is our constraint g. Okay, so we took the partial derivatives of this already in the previous. F was the same function, so we get the same guy out. With this one, the x derivative is only going to come from this term. You get 1. The y derivative is going to come from this term. You get an 18y. And from this term, you get a 2z when you take the z derivative. Okay. So you end up with this equation. That is the constraint again. And then you split this up into 3 equations. So you have a total of 4 equations and 4 unknowns. And to solve this, that's the problem. How do you solve this system? So we start. So before we had the nice situation where like all the right-hand sides were equal, they were all lambda. Here we don't have that. And I thought about it for a little bit to think, well, would it make sense to solve for lambda? Possibly that could work. But there's another thing we can do here, and I should say that like yeah, solving these kinds of systems of equations, if they were linear, there would be a strategy because it would end up being a linear algebra problem. But because these equations are not linear, like you have a product of 2 variables. That's what makes it not nonlinear. I don't believe there's really a general cookie cutter strategy to doing these things. It kind of requires that you stare at things and try things out, and hope that something works. So in this case, what we can do, and what might stand out to you, is noticing that these expressions on the left-hand side, they are quite similar to each other. And in fact, by introducing a variable to each of them, by multiplying appropriately, as I say, you can get them all to be the same left-hand side. So I multiply the first equation by x, the second equation by y, the third equation by z, and I end up with this. Okay. Now, when we do so, there is one thing that immediately should kind of one thing that you need to be aware of, which is that when you multiply, you have to be careful about, well, what if the thing you're multiplying is equal to 0? What if x is 0, y is 0, or z is 0? Then you end up just getting the equation 0 equals 0, which is, it's always true. Usually it's not helpful. So that's just something to kind of keep track of, is that, you could have that you've multiplied by 0, and that has kind of done something to the system of equations in a bad way. Like, it may have deleted some data, because originally you had an equation that told you information, that actually constrained parts of the solutions. When you multiply an equation by 0, that gets rid of that constraint, basically. That means that you've lost some data. So we want to be careful not to lose data too much. Okay. All right. So let's see. So the next thing I do, I set these two equations, the first 2 equations, equal. So because the left-hand sides are the same, we can set the right-hand sides equal to each other, which is what I do here. And then I move something to the other side. I move this guy to the other side, and then I factor out the only thing I can factor out, which is lambda. So yeah, it gives me this. And so this means that either lambda is 0 or x is equal to 18y squared. Okay. And so now we start our casework. So if lambda is 0, let's think about that. If lambda is 0, okay, so I'm doing something a bit clever here. Instead of looking at this, which doesn't tell me as much, I instead plug into this. All right. So I plug into here, and so that tells me that yz equals xz equals xy equals 0. So all the three of these guys were equal to 0 because, well, you have lambda equaling 0 in this case. And somehow that is bad. No, well, so that would end up meaning at least 2 of the 3 variables must be 0. Yes. Yeah, so I don't know how to explain how I saw that. It's kind of just running through possibilities, maybe. So let's just take like the xy equals 0 case. So either x is equal to 0 or y is equal to 0. But the problem is if you have, say, x is equal to 0, then you could have yz. Okay, and then so then yz, which doesn't include that x, would also have to be equal to 0 by one of these equations. So that means that you have another variable that must be equal to 0. So there must be at least 2 variables equal to 0. You can't make this triple of expressions equal to 0 by only making one of the variables equal to 0. There must be at least 2. And then I say not only that, but there must be exactly 2, because if you made all 3 of them equal to 0, the constraint would be invalid. The constraint would not work. So there must be exactly 2 variables that are equal to 0. I do this because that tells us the subcases. So there are going to be 3 subcases. One where x and y are 0, one where x and z are 0, one where y and z are 0. Those are the 3 subcases. Okay. How did I think I need to zoom out. The constraint. So when you get that x and y are 0, oh yeah, okay, I see. So yeah, because once you have that these 3 equations are equal to 0, we've used up these equations. So the only information we can glean from is going to come from this constraint. So so in the case that x equals y equals 0, we look at this guy, that says that z squared equals 4. Therefore, z is equal to plus or minus 2, and that gives us 2 points, 0, 0, and plus or minus 2 for the third coordinate. If you have that x and z are 0, then this constraint reduces to 9y squared is equal to 4, which I write. And so then dividing by 9 and taking the square root, we get y must be plus or minus 2/3. And so that gives me another 2 points. I should probably be underlining these. Okay. And then the last subcase is y equals z, or y and z are equal to 0. Okay, so like looking at this again, that means that x is equal to 4. Okay, so we had a nice thing where we didn't have to take a square root. We didn't get a plus or minus. We just get a single value. That's a typo. Yeah, that's a typo. X is equal to 0. X is equal to 4. Thankfully, I didn't put that wrong. I just wrote a single letter incorrectly. So x is equal to 4, which means that we get 1 point. 4, 0, 0. Okay. And so that closes up this case, but we had another case. We split off from this originally. So now we consider the other possibility, that x is equal to 18y squared, bringing us here. So if this is the case, then I guess I need to zoom out a little bit. Where do I zoom out to? Was it this equation, or maybe you'll just have to compare because it's a little hard to follow. Or do I have a way to dual side? Ooh, yeah. Where am I? I think it's still on the wrong side. Where is that? There's a way to get a leading page, but I don't remember how you do that. Oh well. So yeah, whatever it is, x is equal to 18y squared. I believe what I do is I get rid of the x everywhere. So, and it looks like I'm using this one because I don't want to have x everywhere here. This would be too much redundancy, I guess. So I would end up replacing x here, here, and there by whatever it was, 18y squared. And so that will give you this system of equations. Gotta get rid of that doubling mode. Okay, this system of equations, and we can simplify this a bit. So, immediately I see that we can get rid of an 18 here, and we can get rid of a 2 here. But I do something a little bit more clever here, I think, is it? We assume that lambda is not equal to 0, because that would fall into the other case. Yeah. So when we consider this case originally, lambda equals 0, that exhausted everything. So we can basically, in this case, we can assume lambda is not equal to 0, because otherwise we're just going to get the same solutions as in the previous case. So because lambda isn't equal to 0 by assumption, we are able to divide by it. Is that what I'm doing? Kind of. I'm going a bit further. I'm going a bit further. Again, this has to do with like a bit of clever realization. Because this is not 0, y times z equaling this non-zero value, that means that y and z can't be 0 either. Because if either of them was 0, lambda would be forced to be 0. So since lambda is not equal to 0, neither y nor z can be 0. That means we can divide by those guys. And the reason I do that is because notice we have a redundancy. We have z's on both sides here. We have y's on both sides here. I want to be able to divide by y and z. And I realized, I guess, yeah, the reason I came to this realization of this lambda not equaling 0 was because I needed to be able to divide by y and z. Otherwise, I guess you'd have to factor things out, and then you'd have more cases to consider. And I didn't want more cases. I wanted simpler sets of cases. And as a replacement, I had more clever reasoning. Okay, so yeah, lambda can't be 0. Therefore, y and z can't be 0. Therefore, we can divide by y and z. Therefore, we can simplify this set of equations further. Now, one of the equations disappears. Why? Which one disappears? These two combine together. So when you get rid of the 18 and get rid of the y, you end up with yz equals lambda. So these first two equations collapse to this one. This equation, when you simplify, you get a 9y cubed equals lambda. Yeah. And then this last guy stays the same. Okay. All right. And now, right, so these two have the same right-hand side. Therefore, we can set them equal to each other. We end up with yz equals 9y cubed. And we can go about trying to solve this. So move something to the other side. And then divide or factor out a y. And we end up with this equation. Okay. So that says that either y is equal to 0 or z is equal to 9y squared. And so, well, we have subcases now. So if y is equal to 0, well, that says that, what does that say? I was looking at this. Lambda is equal to 0, but it also says that z squared is equal to 4. Okay, that's the important part. Z squared is therefore equal to 4. Therefore, z is equal to plus or minus 2. And that gives us these points, which are, unfortunately, points that we already found. So we didn't learn anything new from this consideration. One thing maybe I need to look at. So we knew that y was 0. How do we know that x? Yeah, from here. So it's from here. So y equaling 0, we would plug it back into this thing that started off our case analysis to get that x had to be 0 in this subcase. Okay. So the next subcase is where z is equal to 9y squared. And plugging that into the constraint, which is here, we get 27 plus 9y squared is equal to, wait, no, they don't double up. Okay, that's, I was careful there. So when you plug this in as your z, you end up squaring this guy. So you get 81y to the 4th plus 27y squared. So you actually aren't able to combine them in that way that I was just about to try doing. So we get this instead, and then, well, hopefully you recognize that this is, you can solve this. So you have y to the 4th and y squared. So you can actually, you should think of this as sort of a quadratic, but it's like an extended type of quadratic with a variable substitution, say, well, I guess we could say w. So if you were to let, say, w is equal to y squared, you would then be able to rewrite this as a quadratic. 27 not y, 27x plus 8, well, and let me make it look like a quadratic. 81x squared plus 27x minus 4 equals 0. So by doing this kind of variable substitution, you can then re-express it as a quadratic, solve it using quadratic formula. If you weren't able to spot that this actually factors, you would probably resort to using the quadratic formula, finding solutions for x, and then relate them back because x is equal to y squared. You would get y squared equals whatever values, take the square root to actually find the values for y. That's how you could go about doing this. But I don't rewrite the variable. Instead, I'm comfortable enough just pretending that this is a quadratic, but instead of my variable being x, it's y squared. So I write it into, well, kind of an ordered form for a polynomial, and I just try out. Well, I mean, with 81, there's only a handful of possibilities. And the first one I tried for was the one that worked. So I tried thinking, okay, this is probably going to be 9y squared times 9y squared, and then this 4 with a negative is either going to be 4 times 1, possibly with a negative somewhere, or 2 times 2. And then the question is, how do you make 27 happen? Well, 27 happens if you have 36 minus 9. And so you get 36 from the inner, not minus 9 from the outer. So we ended up needing a 4 and a minus 1 in order to make the 27 happen. That's kind of the way I did it. If you're comfortable with factoring things, then hopefully you didn't. Hopefully you know how to do that. Okay. And then how you go about solving this? Well, this factor, notice that this is always positive, right? Because the y squared is always positive, and this is positive. So this whole thing is positive, which means it can't be 0. Yeah, strictly positive, I guess I should say. This guy is strictly positive. It can't be 0. So this guy must be 0. Then I get this equation. And then, of course, I solve for y, which gives me that. And so that gives me this guy, and I think z was. No, I have to calculate x and z, both of them. So once you have y is equal to plus or minus 1/3, plugging that into here, let's see, y squared is going to be 1/9 times 9 is going to give you 1. So z must be 1, regardless of whether y is plus 1/3 or minus 1/3. So if these defining relationships didn't have a squared on the y, then you would have that the number be different, whether y is positive or negative. So you would technically need to try the values out for both the positive version and the negative version, but helpfully, because x and z were defined with y squared, the square gets rid of the plus or minus distinction, and so we just end up with well, the way we can write it is a bit easier. So let me just talk through this also. So 9 or 1/3 plus or minus, plug it into here, you get 1/9. This cancels, it gives you 2. So yeah, so you do get 2 for x. Right. Okay, so that ends our casework. Yeah, we did all of the casework. We were able to find all of the solutions. I guess I should underline this one. I don't need to underline that one because those were already found in the previous consideration. So now what we need to do is evaluate f on all of the points that we found. F is the function x times y times z. So calculating them for the first few points is pretty straightforward because, well, there's 0 in them. So this actually ends up accounting for 5 of the points, right? 2 plus 2 plus 1, 5 points. And then these 2 points, you have something different. So you could write it in this way, or if you are trying to be careful about things, or if you're not comfortable with the notation, you might instead write it as 2 equations, one with the positive version, one with the negative version. I wrote it like this because I'm comfortable with it. So in particular, these plus or minuses mean that if you take the positive branch, you take it for both. And if you take the negative branch, you take it for both. So that gives you evaluations on 2 of the different points. So this kind of issue it would more arise if you had like say, and this is the thing I'm trying to be careful about. If you had like f of say plus or minus 2 comma plus or minus 1/3 comma 1, something like that. I'm going to erase this in a minute. But when someone writes like this is equal to let's stick it to the same thing, right? So the more standard way of interpreting this, mathematically speaking, is to do like the whole positive branch and negative branch kind of consideration. So in that kind of perspective, this would only be two equations. This would be 2 comma 1/3 comma 1 f of is equal to positive 2/3, and also the equation f of negative 2 comma negative 1/3 comma 1 is equal to negative 2/3. That is the more I think that is the more standard interpretation of this kind of statement. But the issue is that some people, and I think I consider myself among these people, some people would want this to range over all four possible sign conventions. Well, and then of course, then the issue is, yeah, what does this mean? So maybe this doesn't mean anything. So we'll make it worse by getting rid of that sign. So if it's like this, is this two equations or is this four equations? Does this mean two different things or four? Like, is this the evaluation of f on 2 points or 4 points? Because for me, mathematical shorthand, I would prefer this to be 4 points. But I know that I'm fairly sure that people prefer to consider this as being 2 points, not 4 points. So if you ever are trying to write this kind of statement, you have to make it really abundantly clear, like by saying like I mean 4 points for this, and I think I write that somewhere with one of my answers. Yeah, so yeah, a bit of a digression on notation, but so okay, so this statement is actually two statements in one. All right, and the conclusion we can take from this is that the minimum value is negative 2/3 and the max value is positive 2/3, which is the last line here that unfortunately was brought over to this page for some reason. Okay, so that was one of the tricky examples. This is, I think, the other tricky example. Let me check. Yeah, so this is the other tricky example, and this one is similar to your 381. This is a volume of a box. The main difference, besides the surface area quantity being different, the other main difference is that in this example, I'm considering the entire box. Your problem has the box without the top, so you have one less side in your surface area considerations. Okay, so the word problem translates into this mathematical statement that you're maximizing the function v, which is volume of a box. I'm letting the sides be x, y, and z, so it's just going to be the product of all three variables. And the constraint we have, well, we can write down the expression for surface area. So, do I need to draw a picture of this? I'm not sure. Maybe it would help. Okay, that's a terrible picture. How do you draw boxes online? Okay, that's the other way. There's just, yeah, so x, y, and z, let's say. So there are three sets of parallel sides, or faces, I should say. Three sets of parallel faces, right? A front, a back, a top, a bottom, and a left and right. And each of these sides has area, which is the product of two of the variables. So you have two xy's, two xz's, and two yz's. That's the surface area of a box. And all of that is supposed to be equal to 64 square centimeters. Okay, so that is our constraint. This is the function we're trying to optimize. And so Lagrange multiplier method, we compute the gradient of v and set that equal to lambda times the gradient of the constraint, which I guess you could call g. Okay, and so, well, we've done this a lot. we've done taking the gradient of this a lot, so that's the same. With this guy, you see that two of the terms show up for each of the derivatives. So the x derivative gives you 2y plus 2z. The y derivative gives you 2x plus 2z. And the z derivative, this goes to 0, the z derivative gives you 2x plus 2y. And so I wrote that here. And then splitting this vector equation up, and also factoring a 2 out of everything, just to make it look a bit nicer. We get this. Oh, and I also get rid of the 2 here in the constraint. Okay. And then what happens next? Right, so I make the left-hand sides of these three equations look similar by multiplying the first equation by x, the second equation by y, the third equation by z. So that's kind of similar to what we did as like our very first step in the previous example. Okay, so now that we have these, we can set them equal to each other. Set the first two equations equal to each other, and factor some things out, I believe is what I do. Factor out 2 lambda, and then I end up distributing the x and the y in. So you get xy plus xz. I think I move this term to the other side, so I get a minus xy minus yz. Yeah. So we get this, and then notice that these xy and xy cancel, giving you this condition. Xz minus yz, yeah, is equal to 0. And so I don't bother factoring here. That's I think that's okay here because like I could have factored an extra z out, but I think the reason I don't care to do so is because notice that these terms show up here, so it's a bit nicer in form if we just consider things using the variables or using these quantities xz and yz. Okay, so you see that there's sort of cases, but thankfully I think this simplifies a bit. We don't have to consider the cases because the problem works out nicely with this lambda. So lambda being 0 would make all three of these equal to 0, which would make this left-hand side equal to 0, which would give us an invalid constraint. So lambda cannot be equal to 0. So we sort of ran into a dead end very quickly with that case, which made it nice in the way that I lay out my work because I don't have to consider that case at all, or I sort of pretend I don't consider it because I realize it immediately gives us a contradiction. Okay, so what this means then is this must equal 0, which means that xz must equal yz. Okay. And because z has to be some non-zero value, positive value, I guess specifically, because it's a side length, that means we can divide by z. So we get x equals y. Okay. And then I don't go further with that, but I do the same thing by considering these two equations, the second and third equation here. I set these two equal to 0, and I notice that I'll get the same kind of thing happening. So setting them equal, factoring out the 2 lambda, distributing things, moving to one side, or however you want to describe it, you end up with this. And this condition is very similar to this condition. Either lambda is 0, which we just argued is impossible, or we have that xy is equal to xz. And then because x is a side length, x cannot be 0, therefore we can divide, we get y is equal to z. So this shows that x, y, z are all equal, which is quite nice, because then we can rewrite this constraint condition. X, y, and z are all equal. That makes these three terms collapse into one term. The term, it'll be 3 times x squared is equal to 32, which is what I wrote here. And then divide and take the square root to solve for x. You get these values. And, well, because x is a side length, it's got to be the positive value. So we take the positive root. And x, y, and z were all equal, so we actually have that all three of these values have this. All three sides are of this length. And what we were trying to do was we were trying to find the maximum volume. So we calculate the volume. Plugging this into the formula for volume, we end up cubing it. I just, for some reason, decided to simplify the radical expression. You don't have to do it that way. The numerical quantity might be more intuitive for you. So you end up with about 34 cubic centimeters, or you get this radical expression if you're trying to be exact about it. And so, yeah, that's what we would anticipate is the maximum, but because we only get 1 point, we kind of want to compare against some other point in order to verify that that is actually a maximum. So, well, we need a convenient value that satisfies the constraint to check our solution against. So what will be convenient for us is if we let x and y equal 2. And I'm plugging that into the constraint. I think, yeah, think about this one, because this one is just the same but divided by 2. So if x and y is equal to 2, you get 4 plus 2z plus 2z. So you get 4 plus 4z is equal to 32. That is what I write here. 4 plus 4z equals 32. And solving for z, we get z is equal to 7. So we end up with the point 227 as a possible configuration for this box. Well, when you calculate the volume of this box, you get 27, or 28. You get 28, which is certainly less than 34. So that means that this solution we found is a maximum. Okay. I'm trying to remember if yours... I remember the lengths of your box. Your box is not a perfect cube. And that's because you don't have a top in your box. So you end up getting a, I guess rectangular prism would be the right word to use. So I guess, yeah, good luck with calculating those things. The hints hopefully help to some extent. You can at least, if you get the same answer, you can be reasonably confident that you did the right thing. Especially if you are able to detect all of the critical points. With these two, it's too simple. There's only 2. It's hard to know for sure. But with the 14, you can, if you get all 14, you probably did the right thing. Okay. Well, I guess that's it.